Right, well, it gives me now great pleasure to introduce our Eddington lecture speaker, Professor Amanda Karakas from Monash University, who's going to talk to us about heavy elements in red giant stars. Amanda.
Thank you. Okay, let me wait for this to pop up. The lights dim. Right. So it's my great pleasure to be giving the Eddington lecture this year in 2019. I think the topic of my talk today is one that is something that Eddington gave a lot of thought to himself. It's about energy generation in stars, although my talk is really a little bit more about the byproducts of that energy generation, and that is the elements that stars make in their interiors. Okay, so an introduction. It's a cliche to say that we are made from the ashes of stars, but it's a true one. So one thing, I really like this picture. This was taken off the coast of Byron Bay in New South Wales, Australia, and it shows bioluminescence underneath the Milky Way sky, underneath the Milky Way galaxy. It's if you haven't been to see the Milky Way overhead in all its glory, it's not something you can see in the southern hemisphere. It's amazing. However, let's look at what we are made of. If we break down the constituents of the human body by mass, by element, you can see that most of the elements, all of them in fact except for hydrogen, oxygen, carbon, nitrogen, etc., these are made inside stars. So my question is, what stars made these elements? What mass ranges of stars made them? And how are these elements then dispersed in galaxies, or our galaxy, over time and also over space? So this is a question not just of stellar nucleosynthesis, where elements are formed, but also galactic chemical evolution. So they're intertwined stories. Keeps on telling me it can't connect to ED-ROAM. Okay, right. So just to put us all on the same page here, because I'm talking about element formation, I just want you to understand the terminology I'm going to use in my talk. Now, from a theoretical point of view, when I make my stellar calculations, I use mass fraction. So we add up the mass of hydrogen and helium and then everything else, which we call metals, because astronomers are lazy. We are, sort of. There are more ways than one. But I'll also use the spectroscopic notation, which is that square bracket notation. This is something that is derived, so when people take the spectra of a star and they derive the elemental composition, they use square bracket notation. So this is the ratio of two elements compared to the ratio in the sun. And this is what I'll be using. For example, the metal content, because we can't measure all the abundances of all the elements inside another star. We can't really do it even in our own sun. So what we do, so we use the iron over hydrogen square bracket notation as a proxy for the star's global metallicity. Okay. And if we have a metal poor star, for example, that iron to hydrogen is less than 0. Okay. And I'll also use iron to hydrogen as a proxy for time. It's not a perfect proxy for time, but it's good enough for the purposes of my talk today. So I mentioned that we have a beautiful periodic table with all these lovely elements. Astronomers, however, simplistic in our view. We just have hydrogen, helium and metals. And, we can really make a decent stellar evolution calculation of a star like our sun just with this, just with hydrogen and helium and everything else. But of course, this talk is not about just that. I'm, of course, interested in the composition of all of these elements, where they came from. Okay, so moving on to look at... So one thing we use when we talk about this story of stellar nucleosynthesis and chemical evolution is we start with the solar abundance distribution. This is a yardstick by which we can measure element production inside stars. So if you haven't seen it, we can measure this composition quite well for many elements. Not all of this comes from the stellar photosphere. Some of this comes from meteoritic data from very old carbonaceous chondrites, but in general we think this is the distribution we get. So we have atomic mass number on the x-axis, this is total number of protons plus neutrons, and we have mass fraction, so remember that all that adds up to 1 on the y-axis. So we can see here, one thing I like about this distribution, because it's a mix of both stellar physics and nuclear physics. It sort of encapsulates a lot of that. So we can see hydrogen and helium are by far the most abundant, they were made in the Big Bang. There's a descent through to the light elements, lithium, beryllium and boron. I won't talk about those. They're by and large not made in stars. Then we have carbon through to calcium. We see an odd-even effect in the elemental composition. We have a peak at iron. And then we also then see a descent through to the heavy elements. But we also see structure in that too, because you'll notice there are peaks, for example, at strontium, at barium, and at lead, and also platinum. So there's a few features there that we want to be able to explain as well. Of course, our sun's not a first-generation star. Our sun, many stars have died, lived and died, and made elements and put that into the galaxy before our sun was born. So this is, if we look into stars, this is just a schematic of our own galaxy. If we look at stars in, for example, the halo of our galaxy, we measure their iron content. We see that on average it's about an order of magnitude less, so that's -1 in the square bracket notation, less than our sun. So we know that the distribution of elements are different. We also see differences in what we call alpha elements. These are elements with multiples of 4 in their nucleus, like oxygen, magnesium, silicon, sulfur, these sort of elements. We see that the distribution of alpha elements is different in these old stars. Remember, I'm using iron to hydrogen as a proxy for time. So if they're in the halo of a galaxy, they're metal poor, they're old, compared to stars in the disk of our galaxy. Okay, so that's a bit of an introduction. I just want to take a few slides to talk to you through stellar evolution and element formation as well. So when we talk about which stars made the elements in the periodic table, we have to really look at the stars that have lived and died in the age of the universe. Because stars that are still on the main sequence, like our sun, haven't contributed to this story yet. So we're thinking about stars that are more massive than 1 solar mass, and then we have to think about what type of experiences do they have as they get older. And so we know that massive stars that explode as iron core collapse supernova are dominant for a good chunk of the periodic table. And then also evolved low and intermediate mass stars also play an important role, especially for the heaviest elements. And we have this schematic, again, we have population that as stars, after the Big Bang, star formation happened, the most massive stars exploded, started making metals, and so the metal content has slowly increased as a function of time. We also see that we have that where our sun is now, we've already had many of those generations must have occurred before our sun was formed. Now, stars experience nuclear reactions deep in their interiors, so we need a way of moving that material from the stellar core, where those reactions are taking place, into the surface, or at least into space. So there are a couple of different ways that they do this. First of all, with low and intermediate mass stars, which are my focus, they experience mixing between the core and envelope. It's a really complicated process that we're still bogged down in some of those details. And then they have mass loss. They have outflows or winds that remove this material into space. Massive stars that explode, well, I think the explosion says it all. They explode, and that is a very efficient way of moving material into space. They also may have mixing and mass loss. Now, if the star has a binary companion, then that may initiate all sorts of binary interactions, where you may also have mixing, mass loss, and explosions. Okay, so just a brief overview of stellar evolution. So what I'm showing you here is an evolutionary track. So it's actually a theoretical Hertzsprung-Russell diagram. So we have surface temperature on the x-axis, where we have the stars on the right-hand side are cooler, because astronomers are weird. Well, it's a historical artefact, but it's an interesting one. So on the right-hand side, they're cooler. On the right-hand side, they're warmer. And what I'm showing you is the evolutionary tracks of how the surface temperature and brightness change as a function of time for a 1 and 5 solar mass star. Now, our sun's called a main sequence star. It's burning hydrogen to helium in its core. I'm going to use burning and fusion interchangeably, so if that's a bit confusing, let me know. After our sun, it uses up its hydrogen fuel through fusion reactions. The core will contract, the outer layers expand, and it's a giant for the first time. Now, at some point, that helium core will keep contracting and get hot enough to sustain nuclear reactions. And it'll go through a stable phase of core helium fusion or burning that'll last for a star like our sun about 100 million years, factor of 10 less than its main sequence lifetime. Then the core contracts, the outer layers expand, and the star becomes a giant for the second time. And it's on this second giant branch where all the interesting nucleosynthesis takes place. It's also where they lose mass through outflows and winds. Our sun's roughly here now. It's good for us. And the stars I'm interested in are up there, and these will be seen as Mira variables. So these are long period pulsators as well. This is actually a key to their mass loss. I'm not going to talk too much about that. So what do stars look like after they've left the main sequence? We have a picture on the left-hand side that shows a schematic structure of a main sequence star, and on the right-hand side of a star that's exhausted its supply of hydrogen at its centre. So we have a helium core that's contracting, we have an outer layers that are expanding, and how big do they get? Well, this is, again, it's a bit of a schematic, but I can explain. I didn't like I took this from the internet somewhere. It's a problem with things from the internet. I don't always like what their labels are, so I put my own on. So when our sun evolves, it'll become a red giant. So this is the initial mass range, 1 to 8 solar mass. It'll get the centre of the first giant branch. It might get about 150 times its current radius, to give you an indication. When it's a second giant branch star, it'll get bigger, more like 350 times its current radius. So they become really big, really distended, and this is why outflows and winds can happen. You can think about what will happen to our Earth. That's something that I've looked into. Our Earth will probably be swallowed during the second giant branch phase. It may survive that first giant branch phase. Okay, so afterwards, when our sun is going through its final phase of mass loss, it has these long period pulsations. It's also a very bright star. We're talking about maybe 10,000 solar luminosities. So it's very bright compared to what it is now. And because it has this large-scale motion of its outer envelope through stellar pulsations. So this can move material out, it cools, dust grains can form, molecules can form. These are really cool dusty objects. And this is what this movie is trying to show. Most of these stars are some of the brightest stars that you see in the infrared in galaxies, sometimes. These stars are also experiencing copious mass loss, where mass loss rates are up to 10 to the minus 5, 10 to the minus 4 solar masses per year. And then at some point, they lose all of their envelope. You'll end up with a central star that's a white dwarf. And those outer layers may be ionised by that UV radiation, and you might see a planetary nebula, maybe. Planetary nebula formation is actually not as textbook as I'm explaining. We think most come from binary evolution. That's really another talk. Okay. So after, our sun will definitely become a carbon-oxygen white dwarf. It may make a planetary nebula. Whether it does depends on the rates of how quickly that material moves away. If it moves too slowly, then if our sun, it actually depends on the evolution of that central star. If that evolves really quickly to become a white dwarf, it just doesn't have time to ionise that outer envelope. So quickly about the fates of massive stars. So these are stars more than about 12 solar masses. Unlike our low and intermediate stars, they go through various phases of core burning. Carbon, neon, oxygen, silicon fusion process at their centre. They end up with an iron core. This iron core can't sustain fusion reactions anymore, so it collapses. We have a core collapse, supernova, explosion. These stars, I'm not going to talk too much about these stars, but just to point out, these are major element factories for most of the elements, from oxygen through to calcium. So we're already starting to fill in some of that picture. There are also, if you have a white dwarf, so something from our low and intermediate mass star evolution, if it can merge or gain enough material somehow that it reaches the Chandrasekhar mass, so about 1.4 solar mass, it will explode as a type 1a supernova. So these stars are the complete thermonuclear destruction of a carbon-oxygen white dwarf. We actually don't know. Type 1a supernova are really useful for many different aspects of astrophysics, from cosmology to understanding the expansion of the universe, all the way through to galactic chemical evolution, and also stellar physics. But we don't really know what their progenitors are still today. They are likely to be the merger of two carbon-oxygen white dwarfs. They could be when a white dwarf accretes enough mass from a companion, but we don't entirely know. Type 1a supernova, however, are really useful for my story of this where did the elements come from, because we think they roughly made 2/3 of the iron in the universe. And this is also an important part of filling in that picture of element formation. they're often really bright objects and they will outshine their galaxies when they explode. So that makes them easy to detect and why they're so useful for cosmology. Okay, let's just sum up where we are now so we can bring together all our current aspects. And this is really just focusing on galactic chemical evolution from carbon through to zinc. So we're still focusing on up to around the iron peak in terms of the origin of elements. Now we have iron to hydrogen on the x-axis. Remember, this is a proxy for time, so time is increasing from left to right. We have X to iron on the y-axis. Remember, this is relative to solar. It's a logarithmic scale relative to the solar abundance or solar ratio. And we have all of those points are observational data. We have a couple of predictions on here. These are theoretical predictions from single one-zone galactic chemical evolution calculations. Cobalt is a great example here. There are two lines, and those show the difference between using different supernova yields. There are what we call standard garden variety core collapse supernova, and then there are these hypernova that explode with really high energies. So that shows how hypernova contribute in particular to cobalt and zinc and a few other elements. Where do my low and intermediate mass stars come in at this point? They really only, for these elements, only play a part in carbon and nitrogen. They also make fluorine, but that's not shown here. Where they really play their important role is heavy elements. Okay, keeps on telling me about ED Rome, I'll ignore that. So where do we stand right now? So we've summarised the elements up to the iron peak. Massive stars are making the carbon through to calcium, or the oxygen through to calcium. Low and intermediate mass stars are making carbon, nitrogen, and fluorine. And then we have exploding white dwarfs that are making our iron peak, mostly. So now I'm going to focus on elements heavier than iron. Now, you'll notice on this plot there are some horizontal lines, no, vertical lines. I'll try and get my words right. We have some vertical lines, and they are located at n equals 50, and n equals 82, and n equals 126. So the point about these lines are that the dominant isotopes of, for example, strontium and barium and lead, the dominant isotopes of those elements have a magic number of neutrons. What does that mean? It's a bit analogous to closed shells in an atomic system. So that means if you have strontium-88, it has a magic number of neutrons in its nucleus. It has a very small neutron capture cross-section. So I'm already hinting at what's going on. That means it doesn't like to capture neutrons, and you make a lot of it, but it doesn't like to capture anything else, so it builds up there. And all of these peaks you can see are caused by nuclear physics now, not astrophysics, which is, I think that's kind of cool, actually. So, what makes the heavy elements? They cannot be made in general through proton captures or alpha captures, charged particle reactions. They have too many protons in their nucleus, so that inhibits charged particle reactions. Instead, these are built through neutron addition onto iron peak elements. So you start with iron, you bombard it with neutrons under different conditions, and you end up building up heavier and heavier elements. I'll explain a bit more in a minute. We think we've identified two processes in nature, the rapid process and the slow process. And I'll try and convince you there might be a third process in this talk. So how do the S and R processes occur? This shows a section of the chart of the nuclides, which is really what I use more than the periodic table, because I'm interested in the behaviour of individual isotopes. So those black squares, they're stable isotopes, so we have neutrons increasing on the x-axis, we have protons increasing on the y-axis, so we're moving up with different elements. So the black squares are stable and the grey are unstable. And they've also got half-lives on there. So the half-life, for example, of zirconium-95 is 64 days. Now, what differentiates the two processes, the slow process from the rapid process, is that if you have the slow process, it generally doesn't have time to capture, so the rate of neutron capture is generally much slower than the rate of beta decay, or radioactive decay. So let's say you get to an unstable isotope like zirconium-95. This is one where the rate of neutron capture will be slower. So it won't capture a neutron, it'll decay beta minus through to something stable, and that'll be molybdenum-95. And then it'll keep on capturing neutrons. So the S process, it kind of meanders through what we call this valley of beta stability in the chart of the nuclides. Never moves too far away from it. The R process, in contrast, the rate of neutron capture is much faster than the rate of decays. So that means you bombard something with neutrons at really high neutron densities, really high under really short conditions. You move all the way to the right-hand side of that diagram, to the neutron drip line. The neutrons go off and you all decay back. So that really distinguishes those two processes. We think in nature that, at least in our solar distribution, that each contributes roughly 50% each. That's the rough breakdown. So where do they occur in nature? We think there's essentially one main process each. The neutron star mergers is something that was proposed in the 1970s, and I'll have a few slides on those just to show that we think these are probably the dominant side of the rapid neutron capture process in nature now. We aren't sure it's the only one. Maybe you have unusual supernova that can also produce our process. But current supernova models, garden variety ones, can't sustain an arc process, so it can't be that. It must be something else. In terms of the slow neutron capture process, the dominant site are low and intermediate mass stars. And they make most of those heavy elements from strontium through to lead. So just a few words on the rapid process. It really was, there was lots of hypothesised sites up until about 2017, when LIGO Virgo detected the gravitational wave signature from a merging neutron star. This was really a monumental discovery because it also had an electromagnetic follow-up, and we could see the spectrum of this thing. So this really gave us evidence that that neutron star mergers are a site of the rapid neutron capture process in nature. Unfortunately, it's still a little model dependent. I've put some estimates of how much our process material was expelled, but if you try and read the papers, they vary by order of magnitude because there's so much model dependence in going for that spectra of this object they observed to try and estimate anything about the R process. And this is really why the S process is still so important, because it's the best way still of constraining our process models. Until we can measure abundances from something that actually explodes, we really need other ways of constraining it. In terms of the site for the R process, neutron star mergers are definitely important, but what's important here is the rate of coalescence. How often do neutron star mergers occur in our galaxy? And right now, we have estimates from theory, this is binary population synthesis models, and also from observations of gamma ray bursts, and it's postulated to be a power law at T to the -1. If you put that into a chemical evolution simulation, and I'm showing that here, remember iron to hydrogen is a proxy for time, and we have europium abundances. This is predominantly made by the R process. There's almost no S contribution here. And we have observations of stars, and the dashed line shows what you get if you use that T to the -1. It doesn't fit. And either the coalescence times are not, either we don't understand coalescence times, they happen more frequently, or there must be another site of the neutron, of the R process. Groups are still fighting over this. So we've been working on the S process as a way of, if we can improve our models of the S process, it gives us a way of essentially working backwards and constraining the R process. Now, we've been working on the S process for a long time, and even though we've known about, for example, technetium inside stars since the 1950s of heavy element formation in these objects, it's really only been in the last 10 years that quantitative detailed predictions for chemical evolution models have been available. And that's partly myself and collaborators, and there's one or two other groups who are working on this. So it's, even though it's a story with a long history, it's only now we're doing quantitative, essentially, predictions. So the stars I'm interested in, they look something like this. This is a schematic on the right-hand panel. We see this is our, let's call our yellow sphere, let's call this our marble. I'm going to give you an indication of their radial scales. If this was a marble, so a few centimetres across, to reach the outer layers of my red giant, I would have to go about 500 metres away. And everything I care about, all the nucleosynthesis, takes place in those surface layers of that marble. This is where we have our helium burning shell, where there is fusion reactions that can occur that can make neutrons. Now, I mentioned that they're important for various reasons, and remember I mentioned they have mixing plus mass loss, and it's that mixing that makes them important objects. So this shows the surface layers of the marble. Now we're looking at the function of time at a schematic structure. So we have mass. So we can, if we're moving up, we go to the surface. We go down, we head to the centre. And again, these are just those surface layers of my marble. And it's in that helium intershell region, so it's rich in helium, where we have fusion reactions can occur. They're made there. And then they can be mixed to the surface. And this can occur many times. And it's this It's really not the fact it happens once, it's the fact it happens repeatedly, which is why these stars are important. Because once we get neutron captures starting to occur, what I'll show in the next slide, once neutron captures are there, those neutrons are captured by ion peak. Because this happens over and over again, you have repeated exposure of that material to neutrons. So even if you're starting with iron, you can build up very quickly to very heavy elements. And this is how these stars make heavy elements, just through that repeated exposure of burning and mixing. And then, of course, these stars are, of course, very diffuse objects. They're very fluffy outer layers, and that will move material into space. We actually don't know. This is still one of the uncertainties about how these stars make heavy elements. We know that heavy elements are made. They're probably made in these carbon-13 rich pockets. We don't understand how those pockets form. We have theories for it. None of them really are found in canonical stellar evolution models. That's still a problem today. Okay, just to show you that then it's mixed up into the interstellar medium. Okay, so what do our theoretical predictions look like? So I'm taking you up a bit further. These shows, so as I mentioned, we've only really been doing this in the last few years. Even though, as I said, we've known about these stars and we've made some simple predictions, we've only been able to make detailed predictions recently. So this shows proton number on the x-axis versus x to ion again on the y-axis. So I like that way of showing it. And what I'm showing you here are theoretical predictions for two solar mass stars of different composition. So I just want to highlight how much this S process depends on the initial composition of the star and what we can learn from galactic chemical evolution just from this. Now you can see I've highlighted the peaks of strontium, closed neutron shell at barium, closed neutron shell, and at lead, 208, or lead, which also is closed neutron shell. And you see there are peaks there for all of them. You also notice if you go from the solar metallicity red, which are the field symbols, the field circles, through to the metal pore calculation, which is the squares, the black squares, you can see that the distribution shifts. And this is because those metal pore models, you're always making the same number of neutrons, but the amount of ion you have is scaled with the initial composition. So you push all the way up to, first of all, you make the strontium peak, then you make the barium peak, but if you have huge numbers of neutrons, you can go all the way up to the lead peak. And we get that in our metal pore calculations. So what can we summarise from this? That most of the lead comes from metal pore low mass red giant stars. And in fact, we don't even need in our process to be able to match the solar composition of lead. All we need to do is take metal pore calculations, put it into a chemical evolution, and we can match all the lead in our solar system. Barium abundance keeps on increasing as a function of time, because we can see that the peak at solar metallicity is at barium. So barium will keep increasing, whereas lead won't. So we can take these surface compositions and we can integrate them up and we can produce what we call a stellar yield. This tells us how much, for example, barium is expelled by a population now of red giants. Not just one star, but a population of them. So we have initial mass on the x-axis. This is for a whole population between 1 to 8 solar mass. And then what I'm showing with the yellow squares, this is the amount of barium that's expelled into the interstellar medium by each of those different theoretical calculations. The other thing I've done here, I've weighted my calculations, my predictions, by an initial mass function. Doesn't matter which one I use. It's a salpeter for those who know and care. But but what this does, it highlights the mass ranges that the mass range that makes the most barium at solar metallicity, and this is between 2 and 3 solar mass. So it tells us already because we know the mass range, we already know the timescales under which that barium is going to be expelled into the interstellar medium. If it's 2 and 3 solar mass, that means we know it's roughly 2 gigayears, so 1 gigayear to 500 million years. This is the timescale with which, from these stars forming to releasing their barium. Okay, what about the evidence? I mentioned we've had evidence for a long time, but now we have much better detailed quantitative observations. I'm showing this is quite a complicated plot, so I'll take you through it. Again, we have proton number on the x-axis, x to ion on the y-axis. One of my theoretical predictions is shown in blue, and then we have observations. This is from high-resolution spectroscopy in black with error bars, so the observations. I didn't actually make a model for this star. I was contacted by my collaborators, and they said, "Do you have a mass of roughly this, of this composition, and I happen to have lying around, sent it to them, and they made this plot. And we were amazed how good that fit is. Now, this isn't actually about me making good models, I hope it is, but I think this is mostly about nuclear physics at play here. So you can see that the light elements fit very well, and by light I mean less than iron, so less than 56, according to this, according to the number of protons. And we can also see that the peak around strontium, which is shown by zirconium here, that they're at the same peak. They also have the peak around barium, lanthanum, cerium, and also around lead. Lead's actually a bit of an issue. I'll come back to lead. But just to take you through, remember this is that log square bracket notation. That's 10 times more than the solar ratio. It's 100 times more. So this is a very enriched star, and this is self-enriched. This is a post-AGB star, which means it was one of those red giants. It's lost its envelope, most of it, and it's still very bright. We see it in the Magellanic Cloud. So this is a self-enriched object. This is not something that's got its heavy elements from somewhere else. Okay, so I think I'd like to, that's a nice place to end that component. I've got one more short section. I think we've done really well so far with our quantitative predictions, and that I have to point out it's not because of the astrophysical side, because we have still severe modelling uncertainties and the mass loss and the mixing, but it's really because we've had excellent nuclear physics input. There are still large uncertainties. We don't know how neutrons, we don't know how these C13 rich pockets form, and this is something there are various ways of trying to explain them in the theoretical calculations. Some of them work and some of them give the right result, but because we don't find them from canonical calculations, we are not sure exactly. And this leads me to one of the puzzles. I mentioned post-AGB stars. Maybe I should have shown this earlier. So what I'm showing you here is, again, this is an evolutionary track. So we have a HR diagram, surface temperature versus luminosity, brightness. We have a 1.25 solar mass star. I've highlighted where it would be seen on the AGB. Again, very bright, Mira-like star. Loses most of its mass, and then it moves toward the left of the diagram. That's towards increasing temperature. When they're post-AGB stars, which is highlighted in green, they're much easier to obtain elemental abundances for when they're in that phase. Why? Because they're warmer, they don't have molecules anymore. Molecules are really they're painful when they get in the way of spectroscopic analysis. So usually if they're warmer, you have only atomic lines to deal with. So post-AGB stars was a long time seen as the poster child, the best way of being able to constrain the sort of models I do. Now, I showed you, and I thought that's a pretty good match. I think it is a good match for all elements except for lead. When we had one of these objects, we just went, oh, it's a weirdo. I'm not going to worry about it. But then all of the metal poor stars they've observed show low lead abundances. And again, just to point out, so lead is one of those elements that we have really good neutron capture cross-sections for it. So it's not the nuclear physics that's wrong. The astrophysics is really set. What that distribution is set by the neutron density and those thermodynamic conditions. You can play with the thermodynamic conditions where it's all occurring a bit, but you don't change that distribution too much. Everything will pile up at lead. Remember I showed you those predictions. As you go to metal poor, everything piles up at lead. You can't avoid that unless you change those. You can change the thermodynamic conditions a bit, but it has to change a lot, and you can't fix it by doing that. We've tried. You really have to change the neutron density. That's the only way of doing it. So post-AGB stars, and there's one other there's a few observational hints, that maybe those abundance distributions are not an S process now. They are coming from what we call an intermediate neutron capture process. Now, we have an S process, it's a low neutron densities. We have an R process at high neutron densities. We started with the two extremes, or scientists did, because it was easier to deal with analytically. But in nature, why would nature necessarily only have those two extremes? So we think that there might be a burst of neutron production above what we find in S process models in low mass AGB stars, in these low mass red giants. This was actually first coined in the 1970s, but that was left alone for a long time until we started finding these anomalous observations and think maybe it's better fit by what Cowan and Rose found in the 1970s. So I have a PhD student who's run some nuclear network calculations, and she's looked at neutron densities a little bit higher, so more like 10 to the 11 to 10 to the 15 neutrons per cubic centimetre. It's less than 10 to the 8 for the S process. And this is one of the Post-AGB stars now. It's not the one from before, but it's very similar. And we can see that the observations, so these are the red points, her best fit is a thick blue line compared to some other attempts by just using standard S process models. And they can't do it. But she can manage, there's no tweaking here. Yep. There's no tweaking, she can just fit it. Just by running, she didn't have to play with anything here. So we think that it's certainly tantalising. Is it evidence for an eye process? We don't know, it's tantalising. Proton ingestion, so where does that eye process occur and what drives it? We think that if you put protons into a helium-burning region, which is very turbulent, those protons are very quickly made into neutrons. It basically gives you a rapid burst of neutron production if you insert those protons into a turbulent, convective helium-burning region. And I won't go into all the details. No one has really made any models yet of it. This is just currently conjecture. Just want to point out there are one other bit of observation that suggests that the eye process happens in nature. There are these carbon-enhanced metal poor stars in the galaxy. They're in the halo. They're very metal poor. And people for a long time said, but if you add an S plus an S process and an R process together, you can match these observations. So this is one of these objects. We have the red points, the observations, again, extra iron versus atomic number. But it's really difficult to do that. And people have tried just to have this additive process. You have an R process that, somehow something explodes, makes an R process. You add an S on top of that, and you can match these observations. But it doesn't actually work that well, and there's all sorts of extra caveats I won't go into, but it doesn't work. But an eye process can. So these now are simulations at slightly higher neutron density than before, and they match quite well. So if there is an eye process, where does it occur in nature? We don't know. There's possibly low mass, low metallicity AGB stars if they have this proton ingestion episode. Others, it's now become a bit of a hot topic. People have suggested metal-free massive stars, rapidly accreting white dwarfs. If it's a real third neutron capture process, how does it affect the chemical evolution of the early galaxy? We're not sure. One study by Cote suggests it's important for the first peak, but if you take a single-zone chemical evolution model, such as the ones my collaborator and I use or work with, so here we're looking at everything from oxygen to uranium, so we're trying to do everything. Let me just zoom in on one of those panels. This is for strontium in particular. So we have the observational points. We have extra iron to hydrogen versus strontium. We don't need an eye process. We need an S and an R, and we can match the strontium abundance. So this suggests to us that there's no need, the galactic inventory doesn't really need an eye process. That doesn't mean it doesn't happen in a few stars, but it might not play a large role in my story of where the elements came from. So my summary is very quick, so I'm almost done. I think we can fill in this story now. We have red giants make it the S process. Merging neutron stars are definitely a site of the R process. Are they the only one? I probably should have put a question mark there. Contribution of the I process? Don't know. If it might occur in some stars, but how does it affect the galactic inventory? Does it affect the galactic inventory of elements? Don't know. Various sites have been proposed. Some of them are interesting, some of them are a little bit wackier. Some of them may work for my post-AGB stars. It's a self-enriched star. The ones in the very middle poor galaxy, don't know. That's not a self-enriched object, so it had to have gotten its eye process, its heavy elements from somewhere else. We don't know from where. So I'm going to almost finish. I quite like, you've probably seen a number of these on the internet. There's many of them, mostly I don't like. Most of them are pretty dodgy. I can use it if I can use that word. This is the one I probably trust the most. This is showing the distribution of elements showing the elements in the periodic table and breaking it down according where those elements have been formed. This one I like the most, although it's still, even for lead, for example, it's gone 50-50 for dying low mass stars and R process. I'd say it's much more low mass stars. Anyway. So that brings me back to the beginning and the end of my talk. Stars replenish the galaxy with new material, out of which new stars, planets, and hopefully people are made. So thank you for listening, and I hope you enjoyed the talk.
Amanda, thank you very much indeed. That was very interesting. And it's open now for questions. Yes, please.
Thank you. I really enjoyed that. I was struck by the mass fraction curve, the way it just drops off a cliff above lead. And previous magic elements, it went down, but it didn't go down quite so rapidly. What's going on there, or not going on?
Let's go back here. So, well, above these, all of these, so these elements up here are radioactive.
Yeah.
Of course. And there is, I guess, a bit of a stable point around thorium and uranium. Everything in between, they have much shorter half-lives.
Oh, so is it they're being made, but then
they are being made. They would be made, but the thing is, this is the solar. Well, this is. It's called the. So this gets into the being a bit more careful with what I'm actually showing you.
Right.
So even though this is called the solar abundance distribution, it's really the solar system distribution, and those elements are measured in meteorites. So and these elements formed in and so we measure. We take very old meteorites. We determine the composition in the lab, and we say this was. You can do a little bit of a backtracking on radioactive isotopes and elements and work backwards and extrapolate and say that's what the composition must have been at T equals 0, which is solar system formation. Right. There's a little bit of wiggle room there. So.
Okay, thank you.
Yes, please, down the front. Could you wait for the microphone because it's being recorded?
So the Large Magellanic Cloud is clearly an unusual environment because it's interacting with the Small Magellanic Cloud and the Milky Way, and material is being exchanged between these systems. So how certain are you that the conclusion you drew for the post-asymptotic giant branch in the LMC is actually a more general conclusion for post-AGB stars, for example, in the galaxy?
That's a really good question. So people have done a study where, so when they found one or two of them with low lead, they thought, well, that's unusual. What's going on here? So they looked at all of so they had a sample of quite a few post-AGB stars that vary as a function of metallicity. Then they also had some in our galaxy as well. So the galactic, so including the galactic sample, they go from an iron to hydrogen of maybe minus 0.3 down to about minus 1.5. So then they weren't worrying about the galactic environment. They were just looking at what's their initial iron abundance. And that low lead seems to drop off below minus 0.7. So it seems to be more a function of the star's metallicity than it is about its environment, and regardless of where they come from.
Okay, time for one last question if there is. Yes, Don.
You had a note on one of your slides saying technetium was observed in stars.
Yes.
Could you tell me what the evidence is and how robust do you think that is?
It's very robust. So the first measurements of technetium were made in 1952 by Merrill. He didn't make any. He didn't. Today that would have been a Nature paper, of course. He didn't bother with a Nature paper. He wrote it into AppJ with a little note saying he found some technetium lines. Since then, we routinely measure technetium lines in stellar atmospheres. We measure them in low mass evolved red giants, so stars that are long period variables, Mira type variables. These stars have long lifetimes, longer than the longest half-life of any technetium isotope. Now the S process also, and I forgot to mention that, the slow neutron capture path moves through technetium-99 as well. So there's a nice convergence there between the theoretical calculations and what we observe in stars. When they first measured it, actually, there were a lot of explanations to try and explain away that technetium. Maybe it's an atmospheric thing, but now we're pretty sure we see it in a few different types of stars, and our model atmospheres are a bit better. So we think it's quite robust. We don't see promethium. It has no long-lived half-lives.
Okay, let's thank Amanda again for an excellent lecture. Thank you very much, Amanda. Really good. Thank you.